The toy collection domain. In this problem, the robot should bring the different toys marked as colored balls to the child, which is marked as a box. There are 5 locations, 0 to 4. The child is at location 4. Each toy is located in one of 4 locations, 0 to 3. A complex distribution describes the toy's initial location and value, which ranges from 10 to 40. Placing a toy near the child has a utility of the toy's value. The robot has 3 skills. It can pick adjacent toys. Picking each toy is different. The pick only succeeds if the adjacent toy's color is given. This skill accurately reports success or failure. The robot can place a toy it is holding near it. This action succeeds and reports so if the robot is holding a toy. Finally, the robot can navigate to each of the 4 locations. The navigation success probability depends on the destination. The robot stays in the same location if navigation fails. The navigation module noisily reports if the navigation was successful or not. And to conclude about this domain, the toy collection problem is a partially observable domain with probabilistic action effects and noisy sensing. These are common characteristics in robotic domains. The needed skills were implemented and documented, and we used the AOS to solve the problem. In the left corner we can see the gazebo simulation, and in the right corner we see the AOS GUI that interacts with the AOS Web API. Let's talk about the GUI. The AOS exposes a RESTful Web API. We implemented the GUI to assist in the fast development of autonomous robots. Users can generate new domains, debug them visually, and inspect the robot execution in real time or after execution. The robot's belief at any time is visualized using graphs that show the distribution over values of each variable. These graphs are easily filtered. Additionally, users can add a Python script that translates a single state into an image. The GUI uses this script to build a combined image representing the robot's belief state distribution. In the GUI, you can see an image representing the robot's current belief. Rows 1 to 4 corresponds to toys 1 to 4. Each toy has a color. Row 5 describes the robot location. Columns 1 to 4 represents locations 1 to 4. 4 is the child's location. Column 5 displays toys in the robot's arm. Color intensity describes the object location probability. Graphs presents variables value distribution, which can be filtered. At each point, the previous action and the observation received are displayed in text, as well as the current action being executed. This example emphasizes the advantage of using POMDPs. See how actions are selected based on the belief state distribution rather than a single possible state. When the belief state is visualized, we can see the reason in the robot action selection. See how applying probabilistic actions like navigation adds uncertainty to the belief, and how observations focus the belief based on their accuracy. Failed or successful pick actions supply valuable information that reduces uncertainty and assists in future decision making.